So after looking at some of your questions from Monday, I just went ahead and created this video. I'm just going to go through some examples using partial fractions. Again, this is mainly for some of the book problems when you're just practicing, because the book problems are oftentimes way more complicated than anything I'm going to give you, and they're complicated just in the sense of computation. The concepts that we're using are the same. Concepts I want you to understand from this class are how to use this Laplace transform, but just having to do problems with crazy calculations by hand is not something that's really essential. But if you're practicing, you'll need to consider some techniques, and partial fractions is one of them. So again, the general purpose of partial fractions is you have a problem with an expression like we have here, and its denominator can be factored. And it may be easier to deal with this expression if it was not written as a single fraction, but as a sum of a couple terms, each of which is much simpler than the original. So the idea is to, in this case, introduce two constants a and b and determine them so that this equation is actually true for all values of s. Remember, s is a variable, as it can take on many values, but a and b are going to be fixed. So again, this is just a useful tool for various kinds of calculations. For us, the main calculation is going to be simplifying how we determine inverse Laplace transforms. We're going to use formulas to do that, so we need to simplify certain expressions so that we can apply various formulas that are used and designed for these more simple examples. So complex examples can be broken into simpler problems, and those simpler problems can be solved by referring to a table or a formula. This also can be used, you may have seen this before in a calculus class, where you can use it to simplify antiderivatives. I'll show you an example of that too. So we have our expression, and we've identified what it should be equal to. We just haven't identified the specific values of the numbers a and b yet. So how do we determine them? We just put the fraction back together, finding the common denominator. At this point, we want to compare the numerators because they have to be equal. If you have two fractions that are equal and their denominators are equal, then their numerators have to be equal as well. So all we do is we reorganize the numerator as a sum of terms with different powers of s. And then we want to compare those powers to the ones we see on the left side. And if we don't see some on the left side, then those are just zeros. So this is similar to what we did when we had to solve our system of equations for the method of undetermined coefficients. It's the same idea. So we've broken our expression into what's called partial fractions, and now we are determining the constants a and b. So the numerators have to be equal. So we just realized that the s term has to equal the s term, and the constant term has to equal the constant term, and that gives us our two equations and our two unknowns. And you just solve that simply, and you get these values, and then you can just plug them back in, and now you have a new way to write the expression we started with, and this new expression is easier to work with in many applications. So for integration purposes, if I wanted to integrate this function on the left, it'd be easier to integrate the two terms on the right separately, because these are just logarithms. Also, for inverting the Laplace transform, you may actually see this on the left as one of the formulas from our Appendix A in the book, and you can use it. But if you didn't notice that, or you had a table that didn't have that, you could use the basic formulas for our exponential functions by using the linearity of the inverse Laplace transform and just computing the inverse Laplace transform of 1 over s minus 2 and 1 over s plus 3 separately as the exponentials e to the 2t and e to the negative 3t. And then the constants come out front because of linearity. So when you have higher powers of factors, And we're talking about linear factors, so factors like some variable s plus or minus some number. We're going to have an expression where we have some polynomial in s and some power of a linear factor s minus a. Again, it could be s plus 5, it could be s minus 10, it could be any s plus or minus a number. We just introduce n terms. If n is the power, we have to introduce n terms. Each denominator, we increase the power by 1 until we get up to the nth power, and then we just introduce a constant. The idea being the numerators have to stay having a lower degree than the denominators, or the factor that we're dealing with. So since we have a linear factor, constant terms are basically 0 degree polynomials, so we have to use constants. I'm just calling them C1, C2, and so on. The idea is the same. We would put this stuff on the right side back together as a single fraction, and then we would set our numerator equal to whatever P of S is, and we'd match the coefficients of the different powers of S and solve a system of equations. And again, you need the polynomial P of S to have a degree less than n for this to work. Again, if you have a factor of s, you could always take that out first and then do partial fractions, and then when you're done, multiply back through by that extra power of s if you had it. So given an example where we have two linear factors in the denominator, but one of them is squared, we have to get three terms. And each of them has a different constant in the numerator, and then the s plus 1 only occurs once, so we just have one term there. The s minus 4 appears twice, so we have it to the first power in one term, and then to the second power in the next term. Again, we put it back together, and we reorganize the coefficients so that we have a clear s squared term, a clear s term, and a clear constant term in the numerator. And we compare that to the s minus 2, which is really 0s squared plus s plus a minus 2. And we just set those coefficients for the powers of s equal to each other and solve the system of equations. And we get these values by doing that. And again, we just plug them back in, and then we have a simpler expression, at least simpler in the sense of doing what we need to do, which is going to be inverting the Laplace transform. The other kinds of factors you can see are quadratics in the denominator that don't factor because they have complex roots. So for these, you can always identify them from the quadratic formula because they satisfy this condition. B squared minus 4ac is less than 0. This is when we have complex roots. So the polynomial, the quadratic polynomial, won't factor anymore because it doesn't have any real roots. For these, all we're going to do is, because they're a second degree polynomial, we have to introduce a first degree polynomial in the numerator. And we deal with powers in the same manner as we did before. We have to, we're going to have some polynomial in the numerator which is smaller than the denominator. If I have a quadratic raised to a power n, then this degree has to be less than 2 times n, because the quadratic to an nth power is a 2n degree polynomial. So we do it just like we did before. We add all these n terms. The power of the quadratic that doesn't factor increases from term to term. And in each numerator, we're introducing a completely different linear factor. So these constants a1, a2, a3, and so on, b1, b2, b3, b4, so on, etc., are all distinct. And that gives us 2n total coefficients. And when we put this back together, we're going to have 2n equations. So the solution will be unique. So here's an example. We have something in this form. We can have the first term where the denominators to the first power, second term denominators to the second power, and then we just line up, we do the algebra, combining the right side together, and then if you do that, you'll see that you'll have a1 times s cubed plus a b1 times s squared plus a 4a1 plus a2 times s, and then plus 4b1 plus b2. I forgot a parentheses here, but just note that that's there. So those are our four equations. And I've put the coefficients of our s cubed plus 5. I've put in the zeros here so you can line them up and see how we're creating the system of equations. And again, once you have the system, the computer can solve it for you. Again, there's online calculators you can use, or a graphing calculator can do it. Maple can do it. You have lots of options. And then you just, again, we just plug these values back in. So taking this example, if we wanted to compute the inverse Laplace transform of this quantity on the left, we could use partial fractions to write it as these two terms, and then realize that the second term is actually itself a sum of two different terms. And then we can apply the inverse Laplace transform to each of these separately. Now, the first one is one of our basic formulas. We have s squared plus 2 squared, and then an s in the numerator. That's our basic formula for cosine of 2t. The inverse Laplace transform of that is the cosine of 2t. For the second one, we have a power of s squared plus 4, and we have an s in the numerator times some constant. There's a formula in our appendix A which tells us how to figure out this to be negative t sine 2t. The third one, however, does not appear in our table. And I'm just telling you here which formulas you want to look at, and try to maybe pause the video, look at the formulas, and see that you can make these identifications. The first term is cosine of 2t, the second term is a negative t sine of 2t. The third term doesn't fit in our table, so we'll deal with it in another way. So for this last term, we've talked about the convolution formula. When we have an inverse Laplace transform of a product, that's always equal to the convolution of the inverse Laplace transforms of each of the factors from our product. So our term is really just a square of something, but it's not exactly, because we have 5 in the numerator. So we just have to realize which formula we're using. We're using this basic formula, and then we just need to rewrite what we have to look like that. And we have the 2 squared over the s squared plus 4 squared. Remember, the 4 is just the 2 squared. So that's why I set it up this way. So the 5/4 is just a constant. We're using sine of 2t. So this is, inside here is the Laplace transform of the sine of 2t times the Laplace transform of the sine of 2t. So inverting it, we get the sine of 2t convolution sine of 2t. The 5/4 just comes out as a constant. Again, this is defined by an integral from 0 to t, sine of 2 times t minus z times sine of 2z dz. So z is our variable, t is a fixed value. And again, it takes work to do this integral, but you work it out, it would end up being this. So feel free to, if you're practicing, use this as an example to practice. But again, the homework, I'm not going to give you things that are super complicated, but they may take you some time to do. It's homework, so you have time. So in this case, partial fractions helped us break the problem into smaller problems, each which was a little easier. 2 of them we got from a table or formulas. And the last one we used a formula, but that formula is the convolution formula. It required us to do some calculation. So in general, you could have some horrible thing like this, which factors. I wouldn't ask you to ever do something like that, but a computer can factor that for you. And then, and again, computers can do partial fractions too, but not all programs have that built in, but you could at least maybe write a program yourself to do it if you really wanted to, or I'm sure you could find one online even that does partial fractions. There's so many things available nowadays for free. A little bit of time researching, you can find some tools that'll help you. But again, I'm not going to ask you to do anything this crazy. I'm just using this to illustrate how this would work. So there's 3 factors, but they have different powers on them. So we break them up into s minus 1 appears once. It's a linear factor, so it has a constant a. S plus 2 appears twice, so I have 2 terms with constants in the numerators. three terms, I'm sorry, because it's cubed. So b1, b2, b3 are the constants for those. And then we have the quadratic that doesn't factor. So we write it to the first power with a linear factor above, and then we write it squared with a linear factor above. And again, each of these terms, if we were computing inverse Laplace transforms, we could do that quite easily. The first two are just exponential functions. The second two, notice they're powers of an s plus 2, and if you remember, or we have a formula for powers of t give us 1 over powers of s. And when you have shifted powers of s, like s plus or minus something, that results in an exponential times the power of t. So these first two are just exponential functions. If we were inverting Laplace transform, the next two would be t times some exponential, and then t squared times exponential, but we'd have to keep track of the right constants to be in front of these. And the last two, again, we would be able to manipulate these last two and make them look like something from our table. And I'll show you one that is as difficult as I would ever give you to do, which is the first power, or you would run into in your homework on the book, in the book. But again, the idea is here, it's complicated, but you still end up with 7 equations and 7 unknown constants. You could figure them out. So let's just take an example of something like we saw before. Suppose we wanted the inverse Laplace transform of something like this, where the denominator is a quadratic, but it doesn't factor. Because if you look at the formulas in our table, we have kind of linear factors to powers. We have variable squared plus or minus some number squared, those kinds of things. So try to make it look like that if you can. And one way to do that is to use a technique called completing the square, which is just rewrite the quadratic as a square plus a square, or a square minus a square. So in this case, I've just rewritten the denominator as a square plus a square. Now, 3/4 you might say is not a square, but every positive number is a square of some positive number. It might not be a pretty square, but it is a square nonetheless. So we've done that, and that makes it look more like something from our formulas. So we have this inverse Laplace transform. Again, I should have had a -1 here. We're not computing the Laplace transform, we're computing the inverse Laplace transform. So just please make note of that when you're watching this. So what would I do? Well, again, I want to make it look like things in our formulas. So I'm going to keep half with the s, because I have an s plus a half here, and then what's left over is 7/2. But in the next one, our formula, when we don't have an s but we have a constant, the constant has to be the square root of what we see here. So I put it there, and then I take it away by dividing on the outside. Just what we have to do using linearity to organize our information. So this first one is just it's a shift of our cosine formula. Again, square root of 3 over 2 is the constant, so I'm writing it square root of 3 times t divided by 2 inside the cosine. And the plus 1/2 here is telling us that we have a e to the negative 1/2 t. And for the second term, I'm just simplifying the constant out front as 7 over root 3, or 7 root 3 over 3 if you want to write it like that. But it's the same, it's just now it's the sine formula shifted by the half. So sine of square root of 3 times t over 2, again times the same exponential because of the plus 1/2 that we see here. All right, so this is just again a little help for you when you're doing your book problems, and maybe some of the homework. But I think I've designed the homework problems to not require too much algebraic work. I want to minimize that so you can focus on what we're learning is how to use the Laplace transform. So just keep asking questions when you run into something that you're not sure how to do, and I'll answer it.